So the first thing we're going to work on is just going through an entire integral using what's called trigonometric substitution, which is what we kind of started working on at the end of the last class. When we do a problem like this, normally we would want to look to see if like U substitution would work. Parts probably won't, but in this case, U substitution doesn't work well. You can try a couple things, and I don't think you'll find something that works very well. But when you have a square root like this, where you have addition or subtraction within the square root, a lot of times in those instances, you can use what we were doing at the end of class yesterday to kind of get rid of that square root. And so when you do it, you pick an x that's gonna get rid of the square root using trig. So you pick a coefficient and you pick a trig function that will work to get rid of this. So based on what we were doing at the end of class yesterday, what coefficient should we pick to kind of make those cancel out the way that we were getting things to cancel out yesterday? What do you guys think? So the idea is we're going to plug something in for x and we want to cancel the 4 and end up with 25. So to cancel the 4, what should we put in the fraction? What do you guys think? Remember? Yeah, so somebody's saying in the chat 5/2. And so the 2 in the bottom will cancel the 4, and the 5 in the top will get you to match the 25 that's here. And then once you do the algebra we were doing in those problems yesterday, you're going to factor something out and end up with a 1 in place of the constant, and end up with a trig function squared in place of the x. And so if you end up with 1 minus a trig function squared, what should we use? And what we said yesterday is the options would be sine, secant, or tangent. And yeah, in the chat, you're right, you're saying sine. And so this should be 5/2 sine theta. And just as a quick review of what we were saying yesterday, the options are going to be sine, secant, or tangent. So if it's going to become 1 minus sine squared theta, we pick that because we can replace that with positive cosine squared. If it's going to become addition in either order, so 1 plus tangent squared or tangent squared plus 1, we pick tangent because that'll be replaced with positive secant. And then if it's subtraction where it's going to be the trig function first, we want secant squared, or we want secant, so that secant squared minus 1 gets replaced with tangent squared. So the fact that this is in the order of that first one, that it's going to end up being 1 minus a trig function squared, we pick sine because 1 minus sine squared gets replaced with positive cosine squared. Okay, so when we do trigonometric substitution, there are kind of 3 broad steps. Okay, so when we do trig sub, the first big step, so there's 3 big steps, is you pick x. Oops, you pick x. You find dx. So we want to figure out what dx is, and then we're going to do some other stuff too. So given that x is 5/2 sine theta, dx is going to be the derivative of that times d theta. So we get 5/2 cosine theta d theta. So dx is the derivative of whatever x was times d theta. Does that make sense to everybody? Any questions? Okay, and so then we're going to come over to the side and get rid of the square root. So down here on the bottom, I'm going to write the square root part. And we're going to do this like we were doing yesterday at the end of class. So we're going to replace x with whatever we chose. And now we're going to do the algebra and the trig to get rid of the square root. So I'm going to square what's inside the parentheses. So I get 4 times 25/4 sine squared theta. The 4's then cancel. So I get 25 minus 25 sine squared theta. I can factor the 25 out. And then 1 minus sine squared is cosine squared. And the square root of that is then 5 cosine theta. And we kind of glossed over why you don't need an absolute value there yesterday. We're going to continue to do that today, and we're going to talk about tomorrow why it's okay not to have that absolute value. But this is the sequence of steps we were doing at the end of yesterday's lecture. Does everybody follow what I would please ask if there's any questions, because I know this is real weird. Everybody good so far? Okay. Okay, so you pick x, you find dx, you sub in for the square root, so you get rid of the square root. And now we're gonna plug everything in to the original integral. So any x that's not in the square root gets replaced with this x, or with the 5/2 sine theta. The square root itself gets replaced with what we figured out down here. And then dx gets replaced with whatever dx is. So we have 1 over, and then instead of x squared, we have 25/4 sine squared theta. So x squared gets replaced with this squared, but this squared is 25/4 sine squared theta. And then the square root gets replaced with whatever we figured out, which in this case is 5 cosine theta. The dx at the end of the problem gets replaced with this. So we get 5/2 cosine theta d theta. So this part's kind of, it's a lot different from u sub. In u sub, you're trying to like create du or dx or whatever. So you're trying to create du. Here, dx is already in the problem. So you're replacing it with whatever we determined that it was equal to. Okay. Any questions to this point? Okay, now we're going to simplify this. And the most, I think, systematic way to simplify it is to factor out or take out all of the coefficients and then simplify down the trig sub. So 1 over 25/4 comes out, but since it's in the bottom, it flips. So 25/4 becomes 4 over 25. The 5 in the bottom comes out as 1/5. But then the 5/2 at the end, since it's not in the bottom, it does not flip. And this 5/2 stays as 5/2 when you pull it out. And so again, it's not like what you're doing in U sub. You've got stuff that's already there and you're taking out the coefficients that are already in the problem. So when they're in the bottom, they flip. When they're not in the bottom, they stay as they are. Okay, so we take out all the coefficients, and now we're going to simplify down the trig. Well, we've got cosine on top and cosine on bottom. So we're going to cancel those. And we're going to get 1 over sine squared theta d theta as everything that's left in the integral. Okay, any questions to that point on what we're doing? Like I said, please ask, because I know this is weird. Okay, so the kind of the steps in trig sub, the first step is you pick x, you find dx, you get rid of the square root, you plug stuff in, and you simplify down. All right, and that's a lot of stuff for one step, but what we're going to see is that when we go through trig sub, that first big step, that's always basically the same. So once you kind of, like, it's a lot of stuff, but once you get used to it, it's actually fairly easy at this stage. You pick x, you find dx, you do the square root stuff, you plug everything in, pull the coefficients out, and simplify down. And now what happens is you've got this brand new integral. So we're going to act like nothing before this is even there. And we're going to try to figure out how to do this integral. But at this stage, it's in terms of theta with d theta. So this is different from one problem to the next. This could be a basic form. This could be u sub. This could be like the powers of sine and cosine stuff and the powers of secant and tangent stuff. where it is basically just U sub and you're just using strategies to figure those out. But we've got 1 over sine squared. And in this particular case, anyone know what would be a good idea to do 1 over sine squared here? What we would do with that?
Wouldn't that equal cosine squared?
Not cosine, but cosecant squared. And
Yeah.
so because it's cosecant squared, that's a basic form. So we're going to rewrite it as cosecant squared d theta because cosecant squared is one of the basic forms. Does that make sense to everybody? And now we're going to go ahead and simplify down these coefficients. So the 5s cancel, the 2 cancels with the 4, and we get 2 over 25 as the coefficient. Now the integral of that is negative 2 over 25 cotangent theta plus c, because it happens to be that the antiderivative of cosecant squared is negative cotangent. Okay, any questions to that stage? Okay, so this middle part, this is the second big step in the process of trig sub. You do the trig integral. And that could be real easy. It might be easier than the one we just did. It might be harder. It might be like the powers of secant and tangent stuff we were doing yesterday, or the powers of sine and cosine stuff we were doing the day before. It might be impossible. And if it's impossible, it's probably one we don't want to use trig sub on. But it's, you figure out how to do the trig integral. In this case, after we apply a trig identity, it's a basic form. And so we get to here. What's the problem with this? So we've gotten rid of the integral at this stage. What's the problem with this as an answer?
It's in terms of theta, not
yeah, it's in terms of theta, which we kind of pulled out of nowhere. And so we need to now go back to x. And that is more difficult on trig sub than it is in u sub, because what we're doing in u sub is you get an answer in terms of u, and then you have u equals something. When we're doing trig sub, you have theta in the answer, but we don't have theta equals anything. We have x equals this other stuff in terms of theta. So what you end up doing is you draw a triangle. And so we go to this original substitution. My bad. Make that a little more space. So I'm going to add to this top right. But the stuff that I've got on the top right of the screen that I just blocked off, this isn't stuff that we're writing as part of the problem. All of this stuff is the work we're showing as part of the problem. So what I'm going to write on the bottom right-hand side of the screen, that is part of this problem. So we're going to go to the original substitution, the x equals 5/2 sine theta. And we're not going to solve that for theta, but we're going to solve it for the trig function. So given that x is equal to 5/2 sine theta, we know that sine theta is equal to 2x over 5, because you can multiply by that reciprocal, and then I just flip the equation around. But sine theta is equal to 2x over 5. Does everybody see why that's true based on the original substitution? Okay, we're now going to draw an angle in the first quadrant. So we're going to say, okay, theta, we're going to assume is an angle in the first quadrant. And tomorrow we'll talk about why that's okay. But we're always going to go with the first quadrant. And then we're going to draw a right triangle to the x-axis. And we're going to label a triangle based on trig. So we know that sine is y over r, or opposite over hypotenuse. And because of that, we're going to label the y side, or the hypotenuse, as 2x. I'm sorry, the y side or the opposite side as 2x. And then we're going to label the r side, or the hypotenuse side, as 5. Is everybody clear from the trig how to do that? Okay. And so now how could I use this? So what I want to now do is get this third side. How can I use this diagram to figure out the third side?
Pythagorean theorem?
Yeah, Pythagorean theorem. So let's say the third side is a. So a squared plus 2x squared is equal to 5 squared. So a squared plus 4x squared is equal to 25. A squared is equal to 25 minus 4x squared. And then a is plus or minus the square root of 25 minus 4x squared. Because we're in the first quadrant, x is positive. So a is going to be 25, the positive square root of 25 minus 4x squared. It is not a coincidence that this square root matches the square root in the original problem. That's going to happen every time. But you should work it out, and maybe not write out every step of the Pythagorean theorem, but you should figure out what the third side is and make sure it does match what you were trying to deal with in the beginning, if there's a square root. Does that make sense? Any questions? Okay, so we draw the triangle in the first quadrant. Now we're going to look at this. Okay, so that's a good question, Colin. The reason we're going to do this is now we're trying to figure out how to go back to x. So we don't have to figure out what theta is, but what we do have to be able to figure out in this problem is what cotangent of theta is. Well, cotangent is x over y, or adjacent over opposite, because it's the reciprocal of tangent. So we can get cotangent by reading that diagram and doing negative 2 over 25 times the adjacent square root 25 minus 4x squared over the opposite 2x plus c. And so the reason we draw the triangle is because it's the easiest way to convert back to x. Does that make sense to everybody? And does that answer your question, Colin? That was what was coming up next anyway, so good question. Okay, cool. Everybody clear so far? Okay, so this is the first legitimate answer because we've done now the antiderivative and we're back to completely in terms of x. Other than simplifying, we're none. But in this case, you can cancel the 2's and multiply straight across. And we get negative square root of 25 minus 4x squared over 25x plus c. And if we think about it, we could actually work it out. We're not going to. But if we think about it, like taking the derivative of something like this would be a relatively complicated quotient rule. And after some algebra, we would be able to get it down to this. We're, again, not going to choose to do that. But if you took the derivative of this, we could simplify it down to this. Okay, a lot going on there. I want to summarize the third step, and then I want to take questions. So I want to make sure we're clear on what's happening on each step. There's some logic here that's unclear as to why this is allowed. It turns out that it is. We're going to go through the theory as to why we're allowed to do all this tomorrow. That theory doesn't make much sense until we've gotten this process down. So please ask any questions we've got as far as what happened on each step, how do I know to do this, or whatever. Please take time to ask those questions because we need to talk about them, and we're going to do a couple more examples before class over. But feel free to unmute yourself or type a question in the chat. The question can be, what the heck are you doing? That's fine too, but please ask if you have them. I'll take questions and then we'll kind of write out what we did as the third step. Do you guys have any? Okay, we're sure.
I have a one.
Yeah, please ask it.
So we don't use the negative for a.
The negative, I'm sorry, we don't use the negative what?
The answer a. We have positive and negative.
I'm sorry, I'm just not sure what you mean. The negative 8.
The negative for a, letter a.
The negative for little a, got it. We don't use that because we're assuming we're in the first quadrant. So a would be the x coordinate at this point, which would be a positive square root. Now, why we assume we're in the first quadrant, that's not clear. That's the easiest thing to do, and it turns out it doesn't matter, but we'll talk about why that's true tomorrow. But the reason we use the positive a is because we're assuming we're in the first quadrant, so x is positive. Does that make sense?
Yeah, yeah. Thank you.
Sorry, I misunderstood. Yeah. Other questions? Okay, so and again, if you come up with more questions, feel free to ask them or interrupt if there's something I'm doing that's unclear. But like I said, there's 3 broad steps. This first step is always basically the same. You pick x, you find dx, you use that stuff to get rid of the square root, you plug everything in, and you simplify down. Make sure not to forget to plug in for dx. Okay, so you plug everything in and simplify down. Once we're then to here, we've got this integral in terms of theta. We figure out how to do that. That part is inconsistent from one problem to the next. So in this problem, rewriting it as cosecant squared and then using a basic form worked. Some problems we're going to have to do other things in order to do that integral. But we do the trig integral. Then we have an answer in terms of theta. What we then do is we draw a picture and you use that picture to go back to x. And I understand this is like a really big process, but once we get good at it, it turns out it's not nearly as bad as what it looks like. In fact, it ends up being easier than some of the problems we were doing before because there's less creativity typically. So the first step and this third step, those are always basically the same. What we're doing in this first step never really changes. You know, minor things can happen where maybe, okay, those don't cancel or whatever, but you're doing basically the same thing. And then the middle step is different from one problem to the next. That's where it can be tricky. The third step, there are a few other things that can happen here, but you're always going to draw the picture in the same way. And then this and a couple more cases, there's a couple of things that we're going to see here in a minute that can happen, but pretty much the same few things happen every single time. And so once we kind of get used to those aren't too bad either. And so we do need to practice this a lot. Obviously, this is something I think new for almost everybody in here. It's not something that's like real intuitive, and we'll talk about why it works later, but it does get to be relatively routine, whereas the only part that changes from one problem to the next is this middle part. Okay, so I want to do another example, and I went ahead and wrote this one before class. But I'd like you guys to take a minute. So I am going to mute myself and let you guys do it for a minute. I want you to do that first big step. So I want you to pick x, find dx, get rid of the square root, plug everything in and simplify down, but don't go past that integral. So I'm going to give you 2 minutes and mute myself, but see if you can get to the integral that involves theta, and then we'll do it together here in just a minute. All right, so I'm going to start working this out. And like I said, please unmute yourself and ask questions or interrupt me or send something on the chat if you have any questions at all. once we determine to use trig sub, we should let x equal 2/3 secant of theta on this problem. 2/3 because the 3 is going to cancel the 9 and the 2 is going to get us to match the 4. And the way we know to mess with the 9 is because that's where the x is. So we're able to cancel the coefficient of that and end up with the other constant. Secant, because this is going to end up being secant squared minus 1. And kind of like we said back up here, if it's in that form, secant squared minus 1, that becomes positive tangent squared. So we pick secant. Okay, so that's our x. Dx is then the derivative of that times d theta. The derivative of secant theta is secant theta tangent theta. And so we get dx as secant theta tangent, or 2/3 secant theta tangent theta d theta. And now I'm going to go to the side to deal with the square root. So I'm going to go to the bottom left of the screen, but I would do the square root stuff not within the integral. I think it's a lot easier to keep track of. So we've got the square root of 9x squared minus 4. And now we're going to plug in the x. So we're going to put 2/3 secant theta in place of x. And now I square that and I get 9 times 4/9 secant squared theta minus 4. The 9's cancel. The 4 factors out. Secant squared theta minus 1 is positive tangent squared. And then the square root of that is 2 tangent theta. Any questions to there? Everybody good doing that? Okay, so now we replace the x that's not in the square root with 2/3 secant theta. So we're going to make that 8/27 secant cubed theta. And then instead of the square root, we get 2 tangent of theta. And instead of the dx, we get 2/3 secant theta tangent theta d theta. And now we pull out all of the coefficients. So we pull out 4 from the top. The 8/27 is in the bottom, so we pull it out as 27/8. The 2 is in the bottom, so it's really 1/2. The 2/3 is not in the bottom, so it comes out as 2/3. And now we take a step to cancel these out. So the tangents cancel completely, and one factor of secant cancels. And we get 1/secant squared theta d theta. Questions to there? Okay, so I know that that's a lot of work, but that first step, that's that big first step I'm talking about, that's pretty much the same as what we did in the last problem. Like I said, it's a lot of stuff, but once you pick x, find dx, you do the square root, you plug it in, and you simplify everything down. That's pretty much the same every time. Now, step 2 is, okay, we have this new trig integral to do that's in terms of theta. So this is different from one problem to the next. If it was just secant squared, that would be a basic form. This is not that, but does anyone know what we should do with 1/secant squared theta d theta? Any ideas? Yeah, so we're going to make it cosine squared. So that's what we're saying in the chat. We're going to make that cosine squared theta d theta. And then I'm going to take a second to simplify these fractions. So what do we got? We got the 2's canceling. We've got the 3. We'll do this in red. The 3 will cancel with the 27, and that'll get us a 9. And the 4 will cancel with the 8, and that'll get us a 2. So we get 9 halves out there. But we've got 9 halves now, integral of cosine squared. And now that's powers of sine and cosine, but both powers are even. So we're going to use the half angle formula. This is what we were kind of doing at the end of last week. That says, okay, rewrite cosine squared as 1/2 times 1 plus cosine of 2 theta d theta. And now we're going to split this into two integrals. And we get it to there. Any questions to that point? Okay, and the integral 1 d theta is just theta. The integral of cosine of 2 theta d theta is positive 1/2 sine of 2 theta because it's a quick u substitution where u is 2 theta. So you would need a 2 here and a 1/2 out here if we were to write it all out. But we can kind of skip that and get 1/2 sine 2 theta. And now we've got an answer in terms of theta. Okay, so this part from this 1 over secant squared integral to this answer, that's kind of the second step. And that's the chunk of the problem that is different from one problem to the next. Here we get one that's a power of sine and cosine, and we have to use the half angle formula. But we do this trig integral. That part's a little harder on this problem than the one before. Questions to there? Okay, now the third step is to draw the picture and go back to x. So we're going to start with the picture on the right and say, okay, we go to the original trig substitution. Yeah, so somebody's saying, can we explain how to use that, why we're using the half angle formula again? That's just when you get powers of sine and cosine, the idea is you would like to do it as a u sub where u is sine or u is cosine. But if you split off du either way, you can't get du as sine here because there's no sine at all. But if you split off du as cosine, there's not a good way to rewrite the remaining power of cosine in terms of sine. And so neither of the approaches that we want to work works. And so then the half angle allows you to rewrite cosine squared in this form. And that's the strategy that we usually apply. But the reason we do is because both of these are forms that we're then able to actually do. So like we know how to do the integral of 1 and we know how to do the integral of cosine of 2 theta because that's a lot simpler to do than the integral of cosine squared theta. Does that make sense? Okay. All right, so that's why we use half angle formula. Yeah, no problem. And now we're going to go back to x. So we go back to this original substitution. So x was 2/3 secant theta. And again, we solve that for the trig function. So we say, okay, secant theta is 3x over 2. And now we're going to draw a triangle in the first quadrant based on that. And so, okay, we put theta here. And secant is the reciprocal of cosine, which means we can think of it as being r over x or hypotenuse over adjacent. Either way, the r side is 3x or the hypotenuse is 3x. The x side or the adjacent is 2. And now we use the Pythagorean theorem to get this third side. Without writing it out, what we're going to do is take the hypotenuse squared minus this other side squared and then take the square root. That gets us the square root of 9x squared minus 4, which is good because that does match the square root in the original problem. Does that make sense to everybody? Okay, so once we've got the picture, if we go back to the last problem, at this stage, you had this answer in terms of theta, and you had a trig function with just theta inside. When you have a trig function with just theta, that's the type of thing you can read right off of the diagram. So you can get sine, cosine, tangent, cosecant, secant, or cotangent right off of this diagram if it's sine or cosine of theta, or cosecant or cotangent or whatever of theta. If it's this, where it's sine of 2 theta, or if theta is not in a trig function, these are the other things that typically happen at this stage. There are ways to handle that, but you cannot get 2 theta directly from the diagram. Unfortunately, the way trig works is not where you can say, okay, well, it's sine and then times 2. That's just not the case. But what you do have is you have a double angle formula for sine from trig that says sine of 2x is equal to 2 sine x cosine x. And then if you ever came across cosine, cosine of 2x is cosine squared x minus sine squared x. And those are identities we should have learned in trig. And if not, then okay, they're true. I can explain outside of class. We can kind of derive them, I guess. But these are identities we're going to use, especially the first one we're going to use a good bit when we're doing trigonometric substitution. And so sine of 2 theta, we can replace with this. So I'm going to come down here. I'm going to ignore the first part for just a second. And what we're going to do is rewrite sine of 2 theta as 2 sine theta cosine theta. And we could simplify those fractions, but I'm just leaving them so it's clear if we're looking at this later that what I did is I kept the 9/4, I kept the 1/2, and then sine 2 theta got replaced with 2 sine theta cosine theta. And I'm going to leave 9/4 theta for now. And now the only reason I'm doing that is not because we can't have 2 theta in the answer. We definitely can, but we can't get sine of 2 theta directly from the picture. We can get sine of theta and cosine of theta instead of 2 theta. And so now for the second part, and I'm going to leave the fractions just for now in case we're looking at it later. Sine theta, we look at the diagram and it's y over r, or opposite over hypotenuse. And so sine theta is the square root of 9x squared minus 4 over 3x. And cosine theta is x over r, or adjacent over hypotenuse, which is 2 over 3x. Now we got to deal with this 9/4 theta, but does everybody follow where I'm getting this? And again, feel free to unmute yourself or type a question in the chat if we're not sure. Okay, so again, just to kind of recap, sine 2 theta, we rewrote using this identity. So sine 2 theta became 2 sine theta cosine theta. Sine theta is y over r, or opposite over hypotenuse. Cosine is adjacent over hypotenuse, or x over r. Now, so when you have 2 theta in a trig function, we use a double angle formula to get it in terms of theta. And then we have theta inside of trig functions, which we get right off the triangle. When we have theta not in a trig function, we use inverse trig, and we go back to the original substitution. So we go to this equation, the one where we solve the original substitution for secant theta. And what we say is, okay, if secant theta is 3x over 2, theta is inverse secant of 3x over 2. And we use, there are ways to do it where we could say, okay, we could use inverse sine or inverse cosine or inverse tangent, but you always use whichever one you originally substituted. So if you use secant, it's inverse secant of this. If you use tangent, you should say inverse tangent of this. And if you use sine, you should use inverse sine of this. That has to do with the domain restrictions on inverse trig functions. And we can talk about that when we go through the theory of this tomorrow. But if we use a different inverse trig function, it may or may not be right. It depends on which one and what the original substitution is. The way we know for sure it's right is to use the one that we originally substituted. So if this was tangent theta equals 3x over 2, we would say, okay, theta is inverse tangent of 3x over 2. Or if it was sine, theta would be inverse sine of 3x over 2. Since it's secant, it's inverse secant of 3x over 2. And now this is an answer, and we just need to simplify. So to simplify this, we'll do this part in red. The 2's here cancel. The 2 3's become a 9 and cancel with that 9. And this 4 will cancel with that 2 and become a 2. So when we get the final answer, we get 9/4 inverse secant of 3x over 2 plus the square root of 9x squared minus 4 over 2x squared plus c. And that's the answer. Okay, questions on that?
Yeah, where are you getting the 2x squared and the denominator for?
I'm just getting it from what's left over from this. So I had sine theta was this over 3x. So the x is still there, but the 3 is gone. And then cosine was 2 over 3x, and the 3 is gone because it canceled, but that x is there. So in the bottom, I got 2 times x times x. Does that make sense?
Yeah.
Okay.
The 3x's cancel each other?
The 3x's don't cancel. What happened was this 3 and this 3 multiplied together and became 9, and I canceled them with 9.
Yeah.
You're good, but the x's were still there. Does that make sense?
Mm-hmm.
Okay.
Thank you.
Yeah, no problem. And then Colin in chat, you're asking, how did I get inverse secant? So it's back to this equation. So right above the triangle, we have that secant theta is 3x over 2. Within the domain restriction for secant, theta then is the inverse secant of this. And so whenever we're doing it, if you had a different problem where this, let's say it was sine theta equals 2x over 5, then we would say, okay, theta is inverse sine of 2x over 5. And I don't know how much you remember from trig, but there are domain restrictions that correspond to inverse trig functions, and you have to worry about that a little bit, and we'll talk some more about that tomorrow when we go through the theory on this. But you always use the one that you originally substituted, and that satisfies the domain restriction. And that just means, okay, here, since it's secant, you use inverse secant. If it's sine, use inverse sine. If it's tangent, use inverse tangent. Does that make sense? Yeah, okay, yeah, no problem. And the reason you're doing that to begin with is that theta was not in a trig function. So if theta is in a trig function, read it right off the triangle. If theta is outside of a trig function, that's when you want to use inverse. Yeah, no problem. Other questions? Okay, so I want to show you in the shared folder on, or the shared drive on Google Drive, there is, it's folder, under Unit 1, it's folder 6. So Unit 1, folder 6. The first file is called Trigonometric Substitution, and the second file is the solutions to that. So you have worked out solutions. I want to show it to you real quick. All right, so if we're on this worksheet, there's 10 problems, most of which involve trigonometric substitution. A few you have to do U sub instead, and it's kind of to point out the difference between those. What we really need to do is get really comfortable with this process. So, and you need to practice these. I have purposely not put a WebAssign up yet because I really want you to just practice the ones where you have the solutions and you can look at the solutions and make sure you're good. If you're attending live tomorrow, what I would really recommend you do is problems 1 to, so it's sheet 1 called Trig Sub. I really want you to get through the first 5 problems before tomorrow's lecture. If you're watching this recorded later, then before you watch the next video, you should work these first 5 problems. And my solutions are here worked out. As far as I know, there are no mistakes on them, although if somebody finds one where a constant's wrong or something, let me know and I'll let the class know. But you have the worked out solutions to those 5 problems. And you can, at this stage, work all 10 of them. So I just really need you to get good at this process and work through several. Tomorrow, we're going to work through 1 or 2 examples all the way through again, but we're also going to go through the theory behind why this works. Pretty much, we're done talking about trig sub, and it's now just a matter of practicing this stuff. So please do practice it. Tomorrow, we'll try to solidify this process and talk about why it's allowed, but that'll actually be it for trig sub. We'll also talk about some strategies as far as how to know when you should use this. But that's the idea tomorrow. Before that lecture, we definitely need to be good at this process. Okay, so that's actually it for today. If you have questions, feel free to stick around. I teach in a few minutes, so I don't have too long today, but I can answer some questions for the next few minutes if people have them. If not, I hope I'll see you tomorrow, and see you later. Thanks for coming to this one.